Hello, everyone. So today we will be talking about externalization and the week 12 content. Okay, whole week 12 content I'm talking in this today class. Thank you all for joining us. So this is so far the week 12 content. Okay, and last time I was telling about jet transform properties. Okay, and the jet transform likeliness, where it is used, where it is applied. So basically, it is applied to solve the differential equations using jet transform, and its ROC is also important. So I opened one. So solving differential equation using jet transform. So conceptually, using the symbolic workflows, first declaring the equation, solving the equation, plotting, analyzing the results. We have the differential equation in this form. So we have this solving the equations using jet transform. And it is very, very similar to Laplace transform that we have studied so far. So symbolically, we can just have, and this is the rabbit problem population, and this is the population that is able to solve this differential equation. If we analyze the results are analyzed in this way. This is error in approximation. These are the references. So poles are the locations in the complex plane where x of z becomes infinite or zero. For the poles, it is infinite. For the zeros, it is zero. I would like to solve some questions. So two-sided sequences, if you have ROC in the form of this ring, minus infinity to infinity, if it is a ring form, so it is two-sided sequences. So ROC and stability is the system, a system stable, or that is a bounded input, bounded output stable. If the ROC includes the unit circle, mod of z equals to 1. Poles outside or of the unit circle can lead to instability. So if it is all the poles, if it is inside the circle, it is a stable. That's what. So checking the stability, it was ensuring mod of z equals to 1 is within the ROC. And we will explore more on causality stability later. So I have some problem statements. What's the first problem one? So you consider x of n is equals to a power n un, where mod of a not equals to 1. So find the jet transform, determine its ROC. Okay. The problem one is actually step-by-step solution I have written like this. Just determining the first the equation x of z is equals to summation of n equals to 0 to infinity a power n z power minus n equals to 1 upon 1 minus a z power minus 1, assuming the convergence. So if I rewrite this, then it is equals to z upon z minus a, where the ROC is mod of z greater than mod of a. Since x of n is causal, the ROC is mod of z greater than mod of a. I hope my screen is visible. So if mod of a is less than 1, then the unit circle is in the ROC, that is leading to stability. So let's say problem 2, statement and solution. So we have suppose problem which x of n is equals to a power n u of minus n minus 1, which is anti-causal sequence for mod of a equals to not equals to 1. So finding the Z transform and the ROC, the solution outline says that for n less than or equals to -1, we have x of n equals to a power n. The Z transform giving x of z is equals to minus infinity to -1, a power n, z power minus n. So rewriting indices carefully or directly applying the node formula for anti-causal sequences. The ROC is mod of z less than mod of a. So Z transform properties one are like linearity, time shifting, time expansion, and time compression, time reversal, and scaling the Z transform. So if the what linearity states, if Z of x1 is equals to x1 Z, if Z of x2 is equals to x2 Z, then Z of axn plus bxn is equals to a of Z of not Z, it is x1 Z plus b of x2 Z. So ROC is at least the intersection of the individual ROC, possibly which is the largest. So time shifting leads to and time expansion. So x of n minus n naught, the Z transform leads to Z power minus n naught, x of Z. Okay. Whereas time expansion states that x of kn, where k is greater than 1, more complex transformation in Z transform. So which is a key point. Key point is shifting in the time corresponding to multiplying by the power of Z power minus 1 in the Z domain. So time reversal states that if x of minus n, if we do that in Z transform, it is x 1 by Z. So x of n, that is a Z transform leading to x of alpha Z for some scaling factor alpha, which is an interpretation that is a reflection in time domain, that is an inversion in around a unit circle in a Z domain. So this is the first problem statement. I would like you to just think and let me know. So the solution is this. Given z of x of n is equals to x of z, then the Z transform of y on n is equals to x of n minus n. Then specifying the ROC. So using the time shifting property, or remember the shifting might affect the ROC's inner or outer boundary. Tell me what is the solution. Okay, so I'm giving you the step-by-step solution. So first, the time shifting property leads to this first. The ROC if you talk. So the x of n is equals to is causal. Shifting it right by n not greater than 0 still yields a causal sequence. That is the ROC remains mod of z greater than r. So if shifting n not less than 0, remember, it may change the causality. Carefully recheck the boundary. Okay. So the conclusion is the transform is z power minus n naught x of z with the same ROC except possibly adjusted for boundary shifts if the sequence becomes anti-causal. Okay. This is the second problem statement. Okay. If x of z is equals to z of x of n is equals to x of z, determine z of x of minus n. What is that? So just typically seeing the ROC. The ROC is typically 1 upon 1 mod of z that is belong to original ROC or equivalent term. Okay. So the mod of z belongs to 1 upon ROC. That is fine. So Z transform properties 2 is conjugation and the convolution, which is the focus of conjugate symmetry, and the convolution in time leads to multiplication in Z domain. So this is the conjugate property. What does that mean? Z of x of n is equals to x of z. Okay, so if the conjugate is done, So it is leading to x of 1 upon z conjugate, where the star denotes the complex conjugation, this star, which is important for real valued signals. If x of n is real, then uh, this conjugate of x of z is actually x conjugate z conjugate, and the ROC might change due to inversion. So convolution in time. So time is like this. If it is convolution in time, it is a multiplication frequency or the jet transform or the Laplace transform. And the convolution in time domain, which is leading to multiplication in the jet domain. So ROC is nothing but the intersection of the ROCs of x of z and h of z. So example convolution property is x of n is equals to suppose a of n un and h of n is equals to b of n un. Then z of x of n is equals to 1 upon 1 minus a power z minus. Okay. Where z h of n is equals to 1 upon 1 minus b z power minus 1. So z of x of n and h of n is equals to 1 upon 1 minus a z minus 1. 1 minus b z minus 1. So ROC is actually what? Just guess it. Since it is 1 upon 1 minus a z power minus 1 and it is 1 minus b 1 z power minus 1. So ROC is nothing but mod of z greater than max of mod of a and mod of b. So if you have problem statement 1 for this property, show that and also discuss the ROC. So if we have convolution time domain, I have to show this, the multiplication exists in Z transform, and also discuss the ROC. So step-by-step solution is this. So if rearranging the sums, and this is giving them. And ROC is nothing but the intersection of individual ROCs. I hope you understand. Okay, rearranging the sums and we'll have this. So Z transform properties 3. So focus will be causality, stability, and the ROC conditions for both. So if we talk about the causality, a system h of n is, is causal if h of n is 0, if for n less than 0. Z of h of n is equals to capital Z of h of z. That is the ROC of the form mod of z less greater than 1. So rightmost side of the rightmost pole or outermost side of the outermost pole leading to stability in Z transform. And rightmost side of the rightmost pole leading to stability in using Laplace transform. Suppose inside mod of Z is equals to R, the system is causal if the ROC extends outward from the outermost pole. Whereas the stability also is a concern. The impulse response h of n must be absolutely summable. Okay. And the Z domain stability requires ROC to include the unit circle. And if the poles lie outside or mod of Z equals 1, the system might be unstable. So these are some examples for the causality and the stability. Just look at it. I have some bandwidth issues, so I'm just turning the camera off for a while. Okay, so these are the conditions for ROC. So there are some problem statements. Determine whether the system with the impulse response h of n is equals to 2 power n to n, find it is stable or not. So hints are to these two steps. H of z is equals h of z, you have to find and identify the ROC and check if mod of z equals to 1 belongs to ROC or not. Step by step solution is there. Give- I will tell you one video about these filters, because second order system and the filters are very difficult because block diagram. I want you to just go through this. MATLAB example I want to show you. Anyway, we are solving so many problems. So these are the block diagram representation. So for the modeling, basically, we do Simulink. Okay, but I'm not giving you Simulink because if you understand the Simulink, actually, you will have lot of understanding with respect to application. There are two other TAs who are already teaching all these things, so that's why I want you to teach something different, which is not being covered with someone else. So signal editor block. Just let me know whether the sound is coming or not. Sharing with sound.
Hello, Part 3. My name is Michael Carone. I'm the product manager for Stateflow. Hello and
State flow part 3 means it is basically related to block diagram. And
welcome to Getting Started
just to have you a non-interrupted thing, I'm just muting my voice and my
with Stateflow, Part 3. My name is Michael Carone. I'm the product manager for Stateflow. So this is the last part of a 3-part webinar series. What we've been doing is building a state flow chart from scratch and introducing the most important major concepts of state flow throughout the process. So far, we've shown states, transitions, flow charts in part 1, and in part 2, we showed parallel states, truth tables, and temporal logic. And for the third part, we'll be talking about, among other things, embedded MATLAB, simulating functions, and events. So if you have not yet seen parts 1 and 2 of this webinar series, you can find it by going to the Stateflow product page and clicking on Demos and Webinars. Or you can just follow the link that is shown right here. So let's go back to our model and see where we left off. Okay, so this is the model that we've been working with. So let's look at the state flow chart and see what we've done so far. So far we have 2 parallel states.
So these are from the specifically from the state flow. I want you to from filters part. So I'm again changing the video. Why I'm showing the video because it's different. Okay, it's different not as simple block diagrams. So these are converting the virtual bus to vector, then IC, rate transition, signal converter. Okay. I want you to understand filters part. So basically the basic filter is low pass filter. And but so instead of gesture example, I'm going to so these are the tools for signal processing. So an expert's guide to using MATLAB simulating for FPGA and SoC design is also there. But so designing digital filter with MATLAB is my aim. Okay, I will play this video. So I'll play this video for you. Okay, meanwhile, I can just show you what are my questions were there. So if the problem statement is x of n is equals to u of n minus u of n minus 1, 5, calculate x of z and discuss this ROC. So these are the step-by-step solution. You have x of n is equals to 1 or 0 to n less than 2 and it is 0 otherwise. So if we have z transform, so z transform is something like summation of 0 to 4 because it is from 0 to 4. Z of minus n, and it is nothing but giving to 1 plus 1 z power minus 1 plus z minus 2. I have taken your so if we keep the factors, now assume what is ROC, region of interest. So entire Z plane without possibly having Z is equal to 0 or infinity, but typically Z where Z is not equal to 0 or infinity. Since it is a finite length sequence, the ROC is all Z, where except Z equals to 0 or infinity, because it is not practically feasible. So we have problem set and solution sketch. So if the problem we have x of n is equals to del of n plus del of n minus 1 plus del of n minus 2. So if we have z transform as del of n minus k is equals to z power minus k. So summation in time leads to summation in z transform. And x of z is equals to 1 plus z power minus 1 plus z power minus 2. And ours is nothing but entire z plane except z is equals to 0. Some more advanced examples, we will have piecewise boundaries and all. So I have some example, which is a two-sided explanation. Say this. X of n is equals to alpha power n, beta power n, where n greater than equal to 0 and n less than 0, with mod of alpha is equals to mod equal to 1 and mod of beta not equals to 1. Okay. So x of z is equals to summation of 0 to infinity alpha power n z power minus n plus summation of minus infinity to minus 1 beta power n z power minus 1. So carefully define the reason for convergence in each sum. We have problem statement 1. For a signal, x of n is equals to 1 power 1 by 2 power n, where n greater than equals to 0. 2 power n, where n less than 0. Find the Z transform and specify the RC. We have step-by-step solution like this. So for x1 of n is equals to x1 of z is equals to 1 upon 1. These are the solution steps. Okay. For this problem statement. And problem statement 2 and solution sketch is this. Solution outline is also very perfect. So before this problem will come back, and I just want to show you this. How can we use a block diagram for this?
Hello everyone, and welcome to another episode of the MATLAB and Simulink Robotics Arena.
So it actually gives you an introduction for the filter design. Okay, it gives you an introduction for the filter design. That's great to understand since it's very speed. So, little slow. Very little slow. I know it's very speedy.
Hello everyone, and welcome to another episode of the MATLAB and Simulink Robotics Arena. In today's episode, we're going to talk about an extremely fundamental concept in digital signal processing, and that is filter design. And to join me today, I've got Mark Schwab from the Engineering Development Group at the MathWorks. Hello, Mark. Do you want to introduce yourself and tell us why you are the best person to talk to us?
Sorry, my mic was not visible, was not audible to you. It's introduction to filter design using block diagram. So just see.
Was about filter
with application to robotics area
design.
All right, Connell. Thanks for having me, by the way. So I work as an application support engineer for MathWorks, and my domain is specifically signal processing and communication systems. So a lot of the tools that we use in this video, I use on a regular basis in many of my projects.
Cool. Well, welcome to the robotics arena.
Thank you.
So moving on, today's agenda, I'm going to talk a little bit about the motivation as to why we decided to do this video in the first place. Following which, Mark's going to do a little bit of background on filter design and go into the math involved with it. And then we're going to do a software demonstration, and he's going to show us how to design a filter and then implement it in MATLAB and Simulink. And we're going to use the filter design tool for this. And then finally, we're going to do some key takeaways and resources to help you guys do better at your competitions. So starting with the motivation, marine robotics student competitions involve a lot of signal processing, especially in the hydrophone task at Romanation competitions like RoboBoat and RoboSub and RobotX. Uh, but before getting into into time direction of arrival and all that kind of stuff, you need to start small, and you need to start with filter design. By the way, we do have a video on finding the direction of arrival of the signal in MATLAB in the robotics arena, so you might want to take a look at that. So without further ado, I'm going to hand it over to Mark and have him get into MATLAB and do some background and take it away.
Okay.
So go for it, Mark.
Before we get into the meat of this topic, I'm going to go over a little bit of background just to cover the basic mathematics behind filter design. So when working with filters, we're working with linear time invariant systems, and we have an input signal that's passed through the LTI system that contains an impulse or transfer function, and then we receive an output signal. In time, the process that's being computed in the LTI system is called convolution, and this is denoted by the first equation.
Yeah, convolution's not easy.
As you can see, yeah, the equation's quite complicated. This definitely isn't ideal. Common practice in signal processing is to convert everything into the frequency domain. And what this does is this converts the convolution process into multiplication, which is much simpler.
So just stop it at how do you convert a signal from the time domain to the frequency domain?
To convert a signal to the frequency domain, we use the Fourier transform.
Okay.
And in the software demonstration, I'll talk a little bit about the tools that MATLAB and MathWorks products provide to support this workflow.
Okay.
So let's take a look at some of the fundamental filters. Perhaps the two most basic filters are the low pass and the high pass filter. As implied by the name, the purpose of the low pass filter is to preserve low frequency components and to attenuate or remove high frequency noise or unwanted high frequency components. Conversely, the high pass filter preserves high frequency components and attenuates low frequency components.
It's pretty simple.
Two slightly more complicated filters would be the band pass and the band stop filter. The purpose of the band pass filter is to preserve frequency components within a specific frequency range.
Okay.
And then conversely, the band stop filter attenuates frequency components within a specific range.
Okay.
So
these are all pretty simple, pretty common filters in digital signal processing, right?
Correct. These are considered ideal filters. So typically when we have ideal filters, they're not the best choice for application. They're more for analysis and
theory.
And theory. Yeah, they're more for analysis and theory.
Okay.
So without further ado, let's go ahead and jump into the software demonstration. Alright, so the data that I chose to use here is actually data recorded from a submarine ping sensor from one of the robotics competitions.
Okay.
Alright, so let's go ahead and load in this data real quick. So in the workspace, you can see what I'm loading in. Y denotes the data that was recorded from the ping sensors, and T denotes a time vector, and then noise is the noise that we're going to add to the signal to filter out, and then duration is just the time of the signal.
And just to clarify, this noise is something that you're adding in just for the purpose of the demonstration, right?
Yeah, for the purpose of the demonstration, I generated a random number generator that creates random noise.
Okay.
So there's the uncertainty involved, and we're going to talk. And in real worlds, it's hard to predict the noise that's going to happen. So this is supposed to mimic a real world application.
Okay. Cool.
So let's go ahead and take a look at the recorded data and time. As you can see, there's 3 distinct pings that the hydrophone has the task of identifying.
Correct.
So next we're going to add the noise that I mentioned to the signal and then compare the original signal in time with the noisy signal.
Oh yeah, I cannot recognize the signal anymore. It's just random noise at this point.
Yeah, so as you mentioned, the signal is almost indecipherable. There's a little bit of correlation, but even where they look slightly similar, there's an amplitude offset.
Correct.
So apart from converting convolution to multiplication, analyzing signals in the frequency domain is also beneficial because it can make plots like this a little more clear. So let's go ahead and convert the signal to the frequency domain as I mentioned before and see if we can get a better idea of how we can filter out some of this noise.
Just before you do that, this FFT function is that the Fourier fast transform that you were talking about that converts converts signals from time to frequency domain?
Yeah, in
Okay.
MATLAB, FFT denotes the fast Fourier transform and will complete the task of converting the signals to the frequency domain for us.
Okay.
So we're going to go ahead and convert both the original signal and the noisy signal into the frequency domain. And then take a look at the two so we can compare. As you can see, analyzing the signal in the frequency domain gives us a really good idea of the significant frequency components from the original signal and where the noise is present. The pulses that we can see around 50 kilohertz and 125 kilohertz are the 2 main frequency components of the original signal, and then the bands of dense frequency components would denote the noise. You may be wondering why there's 2 distinct bands where the noise are present. In robotics competitions, there are pretty common sources of noise. One obstacle that many competitors face is the noise generated by the motor of their own robots often distorts their information.
Correct. Yeah.
And this would be denoted by the low frequency noise that lies within the audible range of 22,000 kilohertz.
Correct.
And then the high frequency noise could be denoted by other robot sonar or other extraneous factors. All right, so let's jump into designing a filter and open the Filter Designer tool. The Filter Designer tool allows you to design filters via radio boxes, drop-down menus, and text boxes. And all of these lie within specific components like the response type, the design method, the filter order, frequency specifications, etc.
Correct. And just going back to when you were talking about the background, I can see it's got the low pass, high pass, band pass, and band stop. So yeah, we actually mentioned those filters earlier in this presentation.
Yeah, and in each one of these drop downs, there's slightly more complicated methods to implement the low pass, high pass. Because as we mentioned, ideal filters are not useful in application. So there's slightly more intelligent filters provided.
Okay.
Also, this tool implements several algorithms. As you can see in the filter order, the minimum order box is checked. This implements an algorithm that will generate a filter of the minimum order based on your specifications. This tool also provides another feature that allows us to observe several different response types for the filter. Some of these response types are the magnitude response, the phase response, group delay, phase delay, impulse response, step response, and the pole zeros response. There's several other options, and if you're interested in learning more about them, I'd recommend looking at the documentation for the Filter Designer tool. So now let's see if we can go ahead and design a filter to attenuate some of the noise. As I mentioned earlier, our signal is being sampled at 300 kilohertz. So let's go ahead and put that in. And then since we're using a low pass filter, we're going to try to preserve some of the low frequency noise and attenuate out some of the higher frequency noise. So taking a look at the plot of our noisy signal, we can see that there's noise somewhere above 125 kilohertz. So let's go ahead and set the pass band to be up to 125 kilohertz. And then in real filter application, square waves are not practical because the filter needs some time to drop down to the stop band. So we're going to need to give the filter a little bit of space to reach the stop band. So let's give it around 2.5 kilohertz and set this at 127.5 kilohertz. And then we'll design our filter. Okay, so this looks like a great filter. Now that we have the filter, you may be wondering, how do we actually implement this in MATLAB? The Filter Designer tool provides the option for us to export the filter as an object to the workspace. To do this, you navigate to the File tab and then go down to Export. A dialog box will pop up giving you a few options. For simplicity, we're going to export this as an object. We can go ahead and keep the default name. Now if you go to the MATLAB workspace, you can see we have an HD object. We have an HD filter object. The way to implement this filter is to use the filter function. As I mentioned, we chose to export this as an object for simplicity because then the filter function only replies the filter object as an argument and then the signal we're filtering.
Okay.
And then for analysis, we're going to convert this filtered signal into the frequency domain. Let's compare the original signal and time to our filtered signal and time. So looking at this plot, maybe our choice of filter parameters were not the best, or maybe even our choice of filter was not the best. So let's look at the frequency domain and see where we might have gone wrong. So as you can see, we did a good job of attenuating the high frequency components, but almost as expected, we still have that low frequency noise. And then from the plot and time, we see that the noise is still enough to drastically distort the signal.
Correct.
So let's jump back into the Filter Designer tool and see if we can do a little bit better. So a low pass filter might not have been the best option because there's low frequency noise that we cannot remove from the noisy signal. So let's see if we can try one of the slightly more complicated filters that we mentioned earlier. So let's take a look at the bandpass filter. Since we were able to attenuate the high frequency noise successfully using the low pass filter, we're going to use the same parameters for the pass band and the stop band on the higher edge of our filter. So let's pull up the frequency plot to see if we can identify parameters that will be successful in attenuating all of the noise. Looking at the noisy signal, we can see that there are significant frequency components from the original signal slightly below 50 kilohertz, and that the noise is within the audible range, so it's probably somewhere less than 22 kilohertz. So let's go ahead and set the stop band to be a little over 22 kilohertz. And again, let's give the filter some time to rise to the pass band. So now we have a filter that looks like it'll preserve a specific band. So let's export this to the workspace and see if this yields the desired result. So when exporting variables, if there's a variable of the same name, you're going to want to choose to overwrite the variable or else you will receive an error. So let's export this and then jump back into our code and implement this new filter. Alright, so looking at the signal in time, it looks like we did a good job. So let's
Yeah.
go ahead and confirm that by again looking at the frequency domain. In the frequency domain, this looks great. We have all the same significant frequency components from the original signal. But perhaps we could even do a little bit better. So let's go ahead and go back into the Filter Designer tool and take a look at some of those other analysis options that I mentioned earlier to see if this filter is actually optimal for our workflow.
So before we move on, what's the first place that you start when you want to sort of look at making these filters better? What is the sort of first plot that you go to?
So the pole zero plot's a very useful plot because we'll go ahead and take a look at it and I'll describe that a little more. So the pole zero plot, as mentioned in the name, provides the poles and zeros, and this gives an idea of what the filter, this gives us an idea of what the order of the filter is. As you can see here, there's 304 poles. So that means that the order of filter is 300.
That's not too good.
Yeah, so that means the order of the filter is 304.
Yeah.
And for implementation and hardware, that would use an unnecessary amount of memory. So let's go ahead and see if we can change our filter a little bit to reduce the order. As you can see, the option for FIR is chosen in the design method. FIR filters are beneficial in the sense that they're theoretically simple. IIRs are slightly more complicated theoretically, but this provides a better result in terms of filter order. So let's choose the IIR and see if this improves our filter.
Oh yeah.
Okay.
It's down to 86. Yeah.
Yeah, so now we see that the filter order is around 172, since we have 172 zeros. So this is much better, but this would still utilize a very large amount of memory. So let's see if we can choose another type of IR filter to improve our filter even more. For more information on these types of filter, I'd recommend taking a look at our documentation. I'm going to go ahead and choose the elliptic filter as somewhat of an educated guess and then see what this does. So now we can see that the filter order is around the magnitude of 20, which is much, much better than the 304 we started with.
Yeah. So before we move on, you did mention hardware implementations. Is there a way that I could deploy this filter onto a hardware directly from MATLAB and Simulink, or do I have to take these coefficients and then write code for it standalone?
Of course, yeah. So you mentioned MATLAB and Simulink. I'm going to go ahead and start with MATLAB.
Okay.
Within the Filter Designer tool, if you go to the Targets pane,
Oh, okay.
yeah, there's options to generate code
generate
for
code,
several
yeah.
different hardware targets.
Okay.
There's also, if we go back over to File, the option to generate MATLAB code, and
Correct.
from there, code generation could be used to implement into filters.
Okay.
But we can also export to a Simulink model.
Yeah, I'm interested to see that the Simulink implementation of it, because I know a lot of our viewers are actually using Simulink. So you want to go ahead and show us how to do that?
Sure, of course. So I'm going to go ahead and choose the Export to Simulink option and then click Realize Model. If no model is currently open, what this option will do is open a blank model with the filter block, but I actually already have a model open that implements a similar workflow to the software demonstration we just covered.
Okay.
Alright, so as you can see, a filter block was added to the model I already had open. So before we go, I'm gonna go ahead and connect this block, but before we move further, I'll talk a little bit about what this model does. The model reads in an input signal and then a noisy signal and adds the two signals together. Then these signals are passed through a filter and we can observe the output at all three stages through a scope. Coming down from the scope, you can see a transformed subsystem. I'm going to go ahead and click on that and take a little bit of time to discuss what's going on. So the fast Fourier transform is a process that's computed on a vector of information. But Simulink runs on sample time. So if we were to just simply implement the FFT block in Simulink, the transform would be computed for each sample time. So we would be taking the transform of scalars rather than vectors.
Correct. Okay.
So what we do here is we first use a zero order hold to ensure that our signal is in this discrete time domain. And then we use a buffer to store the signals into a vector.
Okay.
So then we can use the Fourier transform. So then, of course, like we did in MATLAB, we take the Fourier transform and then take the absolute value to analyze the data. And then we use a special vector scope that's set to analyze the data in the frequency domain. Let's take a look at the results of the Simulink model to ensure that they're similar to the MATLAB code.
Okay.
So first we'll take a look at the signal and time through the scope. So as you can see, it's clear that this is very similar to the signals that we had in MATLAB. So let's jump over to let's jump over to the signals in the frequency domain and ensure that that's also. So since we have three different vector scopes, there's going to be three different vector plots. The vector scope does not support multiple inputs, so we cannot stack plots like we did in the scope block.
Okay.
But as you can see, again, the signal in the frequency domain also pretty strongly correlates the signals from MATLAB.
Okay. Cool.
If you would like to follow the same workflow without using the MATLAB interface, the Digital Signal Processing Toolbox also has a block used to generate digital filters.
Okay.
To find this block, let's go ahead and go into the library. Okay. To find this block, navigate to the DSP System Toolbox, choose Filtering, and then choose Filter Implementations, and there will be a Digital Filter Design block. So let's go ahead and drag this into the model. To use the Digital Filter Design block, double-click on the block and a graphical user interface identical to the one we used in MATLAB will be presented.
Okay.
In implementing this block, you do not have to worry about exporting to Simulink. When you click the Design Filter button, those filter parameters will automatically be uploaded into your Simulink model.
Okay.
As I mentioned earlier, there's also the option to generate code for hardware in Simulink. To learn more about this, I'd advise taking a look at the documentation. Alright, so now let's go ahead and jump back to the presentation to look at some key takeaways. So the Filter Designer tool allows for an iterative design, and this is beneficial because in competitions, the competitors likely won't know the parameters that they want to use to their filter, so they're going to have to use a trial and error approach to really reach the best filter for their robot.
Okay.
Implementation for filter design is available on both MATLAB and Simulink, and hardware implementation is also available on both platforms.
Okay, well, thank you so much, Mark, for taking the time out to come and share this information with us. Before we wrap up with this video, I'm just going to go ahead and point you guys to some resources like we do always. Again, we've got a lot of video content available and a lot more to come. Please write us and tell us what you think about it, and you can get in touch with us either on our either at the robotics arena at mathworks.com or on our Facebook group. And then also don't forget about the software offer. We do offer free MATLAB and Simulink with around 70 odd products um, uh, to student competition teams. So please take advantage of that offer, and you can get access to tools like the filter design tool and a bunch of other tools. Um, and finally, we're also filling up the robotics section of the Racing Lounge blog. So uh, don't forget to take a look at that as well. Um, and thank you so much for watching another episode on the robotics arena, and we hope to see you again.
So the question is determine whether the signal xt is equals to sine 3t is periodic, and if so, find its fundamental period. So the solution consists of sine omega t. Okay, the period is t is equals to 2 pi by omega. And if here omega is equals to 3, so t is equals to 2 pi by 3. Sorry for the disturbance. So here we have the signal is periodic with the period t is equals to 2 pi by 3. Problem number 2 on the topic 4 is this: if this is the signal xt is equal to e power minus t periodic, and if yes, explain. See the solution steps what I have written. Since x t plus capital T is equals to e power minus t plus capital T should equals to e power minus t, isn't it? So that implies e power minus t should be equals to 1, which is true only when t is equal to 0. Okay, since a non-zero period does not exist, therefore xt is equals to e power minus t is non-periodic. Okay, or aperiodic. That's what our ambition was. So if I say basic operation on signals theory, so this is about recap, because we have covered almost all the questions and solutions also. So we have x of t minus t naught, shift the signal by t naught. X of at is actually scaling. If a is greater than 1, so it is actually compression. It seems like it's a decompression, but it is a compression. Signal can be superimposed, that is a addition. Mathematical expression is yt is equals to 2x of t minus 1, which is amplification and delay. So let's say some problems. So given xt is equal to t square, find the shifted and scaled version of which is yt is equal to 3 xt minus 2. Think about it. Think about it. So we have solution steps as substituting t minus 2 into xt, because we have a problem statement xt is equals to 3 xt minus 2. Okay. Scale by 3, then yt is equal to 3 xt minus 2 whole square. This represents the original quadratic signal shifted to the right by 2 units and scaled by a factor of 3. Coming to the problem 2, given xt is equals to e power minus tut, determine the time reverse signal where yt is equals to x of minus t and discuss its domain. So we have time reverse signal yt is equals to x of minus t, which is equals to e power t u of minus t. So the unit step y x u of minus t equals to 1 when t is negative, isn't it? Because ut is positive when t is greater than 0. Otherwise, it is 0. Okay. Since we are talking about u of minus t, so it is minus 1. Sorry, equal to 1 when t is less than or equal to 0. So thus, yt is e power t for t less than or equal to 0 and 0 for t greater than 0. So we have system properties, that is linearity and time invariance. So a system is linear if it satisfies these properties. T, a time variant if a time shift in the input causes an identical shift in the output. So some problem statements. Consider system defined by xt plus 3. Tell whether this is linear or not. Tell. Since the question is about linearity, so it won't affect until unless it is changing the power or the order of xt. So it is linear. Okay, see the solutions. So whatever I told, it's not linear. Why? Because plus 3 is there. That is a bias. Okay. Problem number 2. Topic 6. Tell me whether this is time variant or invariant. So it is time invariant. Why? T is not affecting externally. T is affecting only internally. So for convolution, topic 7, which is a convolution, so we have this problem statement.
Any function convert with delta t is given to that function. Since we have cos ut, cos t ut, and delta t, so any function which is convolving to delta t is given for that function. So convolution for discrete time systems. So for discrete time LTI systems, convolution is defined as yn is equals to x of n convolution with h of n, where it is defined from summation from minus infinity to infinity x of k, h of n minus k, which is very similar to the continuous case, commutativity, associativity, and distributivity. So for a given sequences, x of n is equals to 1, 2, 3. For n is equals to 0, 1, 2, where h of n is equals to 1 of minus 1 for n equals to 0 to 1. So compute x, phi of N is equals to x of n convolution with h of n. So write out the convolution sum. For computing for different n, we're getting this 1, 1, 1 minus 3. So enough problem, more than 20 problems we have solved so far. So I'm sharing screen. So there are some questions which I'm showing for a signal. So you have solutions. What are the solutions? So far we have seen several questions, and I would like to end the session. Thank you so much for joining. And for more results, for more analysis, please refer my PPT, which is attached. Thank you. So this is a problem statement, which is compute the jet transform. So these are the solution outline. Please find this. One last problem of inverse jet transform. These are the factor out coefficients. And the final solution is xn is equals to this. I'm giving you the solution patterns.